Okay, hi, I'm Metta Spencer. Today I have a real coup. I have managed to finally capture Paul Beckwith, whom I've been pursuing for a long time. I really want to talk to this man because he's an expert on climate, and I lie awake at night worrying about the climate, as you better too, if you know what's good for you. We all have to start worrying about that. So Paul lives in Ottawa and teaches now and then, or sometimes, at the University of Ottawa, and does a whole lot of research and makes a lot of videos about climate in particular. So I'll tell him now what I've been lying awake worrying about, and he will probably have some answers for me. At least we can get into the issue. Okay, here's what's bothering me. You know, there's a guy, not one person, but a whole pile of researchers in Zurich at something called the Crowther Labs. And they came up with something several months ago, a kind of a map of where in the world it's possible to plant new trees. The idea is that we now have 3 trillion trees on the planet. We need another 1 trillion trees. And if we did that, we'd be able to reduce the carbon emissions that we've already put into the atmosphere, suck it back out again and put it underground, about 2/3 of it. So we'd be well on our way. But the point is we have to get busy on it and start doing it quickly. And I think the point is, not only should we do it quickly, but we better know what we're doing, because I think it's possible to make some mistakes. The thing that worried me when I looked at their map of where to put trees, you see what they did is they calculated how much land there was in hectares on the planet, and then they subtracted the amount that's already planted with forests or covered with forests, and they subtracted the amount for cities, and they subtracted the amount for cropland, which left them with something close to 1 billion hectares of land that they say would actually be able to support forests and would grow there. But my problem is a good part of that, a substantial amount of that, is in the Arctic. And I had been reading and watching videos by a couple of guys named Zimov, who live in the eastern Siberia and have something called Pleistocene Park. And they are really opposed to having trees in the Arctic. They go around with their trucks and push down every sapling they can find, and are trying to import big animals to not only knock over a tree before it has a chance to get going, but to stomp on the snow and push it aside and help keep the soil cold, because their fear is that the permafrost is melting, and they think that trees are largely responsible for that. I think clearly because of the albedo effect, that is to say, when light comes in, it hits the snow, bounces off, and therefore the ice, the snow, keeps the ground colder than it would be otherwise. But they have trees, and trees are dark, and dark things absorb light and heat. So the trees are warming the soil. There may be, and I don't know that I've got enough evidence on this, I certainly don't, but there's a guy named Ian Hartley in Britain at the University of Sussex that has been doing research on permafrost. And he says that he's measured the soil temperature in at least one forest, a birch forest in Finland, and compared it to the soil just on the other side of the forest. And the soil is warmer in the forest. And he thinks, at least the kind of suggestion he made slightly in his article, was that maybe the trees are doing something more than, affecting the albedo. Maybe they're helping the decomposition of the soil and speeding it up that way. So there may be 2 ways. I don't know whether he's sure of this, but there may be 2 ways in which trees are good. Okay, my theory is we better, avoid putting trees where there's permafrost. Unfortunately, 55% of Canada gets permafrost. and about the same amount of Russia gets permafrost at some points of the year, and 85% of Alaska does. So that means that if we are to avoid planting trees where there's permafrost, we have to cut out an awful lot of acreage. And then the question is, how can we make up for that elsewhere, if at all? So that's my problem, Paul. So now you're let's see what you think about these things. Am I goofy?
Well, you're only talking about 29% of the planet surface area, right? I mean, was there any mention of the oceans in all of these articles that you've read?
No.
So this is a problem. This is a problem. I mean, why don't we capture the carbon in the oceans?
I'm not objecting to that. I mean, if you've got a solution, I want to hear it.
I mean,
algae would do it. Algae will capture it, right?
Yeah, exactly. We need, kelp growth. We need seagrass growth. We need mangroves. This is along coastlines. Mm-hmm. And we need phytoplankton. And the phytoplankton are lacking iron in a lot of cases. There's areas of the ocean that are high nutrient, low chlorophyll, because the phytoplankton are missing an essential ingredient, which is basically an essential nutrient, which is basically iron. So normally they get the iron from dust that is blown over the oceans. For example, the trade winds that are carrying dust from Africa, from the deserts, the Sahara, etc. They blow this dust over the oceans, and the iron content in the dust stimulates phytoplankton growth. So, yeah, I think there's a very easy solution to all this, and there have been people that have looked at iron seeding in the oceans. One of the most famous or infamous experiments was Russ George in 2012, I believe. Had 150 tons of iron sulfate in the ocean, put in the ocean offshore Haida Gwaii, the Vancouver Islands, and it stimulated massive phytoplankton blooms, and the salmon fisheries returned and hit record high levels for 3 years running after that occurred. So, it's very controversial, but we have to look at the risks of proceeding, with climate change out of control, for accelerating rapidly, and compare the risks of that, which are enormous, to the risks of actually trying to pull CO2 out of the atmosphere in a vast quantity from the ocean. So, I mean, this is one of my problems with scientists in general, is just their way to over specialize. So how can people write entire papers on the idea that we need to plant 1 trillion trees on the planet to suck out carbon, and they don't even mention the ocean at all? The other thing is, you said that, I thought Scientists for Peace and, lying awake at night, I thought it was all on the nuclear winter scenarios, because there's an interesting connection to some of the wildfires that we've been getting recently. Right? Some of these wildfires are burning over such a vast area and so hot that the convection, the convective uplift is carrying ash particles right up into the stratosphere, and then they do start affecting climate. And it talks about some of the, it's a recent phenomenon that some of these so-called firestorms have enough energy and heat to carry particles right up into the stratosphere. Before, it was, mostly attributed just to volcanoes, for example, or to, nuclear detonations in cities, or firestorms in cities. You can talk even about World War II firestorms in some of the cities, and how, those actually were climate changing events, because they lofted ash up above the top of the troposphere, which is, where weather occurs. You go up above the troposphere, there's no rain to wash these things out. So they can stay up in the upper atmosphere for long periods of time. Also, because they're dark, ash and soot and carbon-based materials that are dark, the sunlight heats these particles. So they they get lofted even higher because of their heating, right? So they can stay up for tremendous amounts of time because of this phenomenon. And this is all, this is basically the nuclear winter scenario that we were very concerned about, during the Cold War. And, people forget about this. I'm sure you don't, but.
No, because it's been revived repeatedly since then. In the last 10 years, there have been additional studies about nuclear winter and confirming pretty much what they thought,
Yeah, yeah. It's actually worse. There was a book, there's been a lot, like during the Cold War, it was being recognized by a lot of scientists, and they tried to get this information to world leaders, calling for bans on, nuclear proliferation and even getting rid of existing things that we have. But even 10 years ago, Alan Roebuck is a climate scientist and atmospheric scientist, and he has done quite a bit of work in this area. And their studies basically show that, even if it was the small nuclear exchange between, say, Pakistan and India, with, that's a very, those, and with Hiroshima-sized nuclear bombs on cities causing firestorms, that would be enough to basically eliminate 25 to 40% of China's grain crop, both winter wheat and summer wheat, and take out 20% or more of US corn crops, for example. So that would cause a global famine. Mm-hmm. And the information that's come out from the wildfires with the recent paper, and I haven't done a video on this yet. I did a video on the idea of nuclear winter a few years ago, but there's more and more data coming out every time there's a large volcano. It's studied to see how much material it put up. That's mostly sulfur dioxide into the upper atmosphere to cause global cooling for a few years after the event. But these wildfires give us a lot more information, really recent information. And the idea of nuclear winter is a lot worse than we thought even in the Cold War. I mean, the recent studies are showing, yes, it's actually even worse, and would be more of a global threat. Now, climate change, we're talking about sort of, world-changing events, maybe civilization destroying events, maybe even going up to, existential events for humanity. And climate change, is right up there, although it's a very different risk than, it's a very different mechanism than, say, an asteroid impact or a nuclear exchange, right? Those are episodic, very sudden events. Climate change is an ongoing thing that's accelerating, creating ever and ever higher risks to global food supply. And, people are starting to wake up. I think you'll probably agree there's been a change in the last sort of year. Maybe you can attribute quite a bit to, the young people like Greta Thunberg, and getting worldwide visibility on, raising the threat that, look, we haven't done, we're really, we talk a lot, but we have done very little. And if you look at the CO2 level going up, at ever faster rates, right? We're not slowing down the problem. The problem's accelerating. I mean, the latest International Energy Agency reports on emissions show, even accelerating rises in emissions, fossil fuel emissions. So we're going.
Worse than I had heard. But I also, let's go back to these fires, because although certainly I'm familiar with the whole nuclear winter, it's not a debate, it's fact, I guess.
Yeah.
But I had not come across anything about the comparable impact of forest fires. That is news to me. Now, did you say you are studying that yourself?
Well, there has been a few recent papers about that. There's a very good book called Mega Fires. There's a few other books that have been published recently for the general public on fires, the history of fires and the danger of fires. I mean, fires are, talk to people that fight wildfires, and the fires are burning hotter, they're more frequent, they're burning larger areas. And when they burn large areas, they can create very, very strong updrafts. And in fact, even firenadoes, these fire tornadoes, they can generate tornadoes, these intense fires. And then these tornadoes.
What intrigues me is the notion that you have two antithetical effects. On the one hand, there's the heat of the fire, which certainly has to be contributing to global warming. I presume. I mean, you can't have a fire without having something getting hot. But the impact of the smoke into the stratosphere would be a cooling effect. It would be the worst possible way to overcome global warming.
Well, it's a cooling effect, but it's on a very short time scale, right? It's a cooling effect.
Now, what about these things? If the soot or whatever gets up into the is it the stratosphere?
Yeah,
that's where it goes, and the fires are strong enough to push it up there, where normal fires would not get that high up.
That's right.
And then it gets up there, and it's going to stay a while, isn't it?
Yes, it can stay for generally for several years.
Yeah.
Okay, and then be dispersed.
Cooling effect.
Yes. Well, the idea of global dimming. I mean, our industry puts out soot and particulate matter in large quantities, mostly from incomplete combustion, and that soot and stuff goes up into the stratosphere and causes and offset some of the warming that would have occurred. So this 1 degree Celsius increase in warming, or 1.2 over, since again, the baseline is very important. When people say industrial revolution, it used to mean 1750, to now, but now, lots of people just throw that term loosely, and it means, the average at the turn of the century or something like that, or 1850. But anyway, there is the amount of cooling from all of the aerosols that are constantly put up. This is a constant dynamic thing. Like if you get rid of the source, then the aerosols drop out of the lower atmosphere within about a week or so. So they're continuously being put up there by industry, and they cause anywhere from 0.3 degrees Celsius to 1.2 degrees Celsius of warming. Of cooling, rather. So if the aerosols were not there, we would be much, much warmer than we are right now. So it does hide a lot of the effect.
Yeah, I have heard that when scientists, insofar as there is a debate, and I guess there's not much one anymore, but that that any debate that occurs among scientists about global warming mostly focuses on trying to guess or estimate the effects of the aerosol, and how much, if that were taken out of the equation, how much difference it would make.
Yes, that's right.
I only vaguely have a dim understanding of it, but it sounds like something maybe we should know about.
Yes. I mean, it's a very important issue. The idea, what is known as global dimming, the offset from the aerosols, the amount of cooling. I mean, I mentioned the 0.3 Celsius to 1.2 Celsius. I mean, that's a wide range, and some people have actually said it's even higher. It could be a couple degrees, 2 degrees Celsius.
That would be attributed just to the aerosols.
Just to the aerosols, yes, that's right. And of course, there's going to be regional differences because, if you're near a source of a large number of aerosols, the cooling will be larger than if you're, say, in the southern hemisphere, on an island in the Pacific, right? So look at, China, look at India, the heavy industry and the cooking fires and things there mean that the offset of the warming is largest over those continents, right? I mean, eventually these aerosols can get dispersed, but generally they're in the lower atmosphere. So when we talk about a large volcano putting soot and ash and sulfur dioxide into the stratosphere, we talk about these mega fires, these enormously hot wildfires over large areas, creating a firestorm, putting ash and stuff into the stratosphere. Those are different beasts because they're putting the ash and soot up into the upper atmosphere, where it it doesn't get rained out in a week. Gravity has to pull it down to the lower atmosphere, and then it will get rained out when it reaches the lower atmosphere.
Mhm.
But that can take years. And also, if the particles, the aerosols are dark, the sun is heating them up. And when it's heating them up, they're heating up the air around it, and they're buoyant. So they don't settle down. Gravity isn't pulling them down very fast. Some of them are even being lofted higher and higher and higher. And this is what Alan Roebuck, climatologist, has been talking about for many years. And
struggle with this a minute. Maybe you can help me. Okay, on the one hand, this black stuff is going to warm the atmosphere because it's black, and it keeps heat. It gets
warm the upper atmosphere, yes.
Warm the upper atmosphere. On the other hand, the notion of soot or anything like the sulfur
blocking the light cools the lower atmosphere.
Cools the lower atmosphere.
Exactly.
So these fires, insofar as they put this stuff up there, have an overall cooling effect on the surface, right?
On the surface, yes.
Except that they're fires. They obviously are creating heat on the surface.
Yes, they're creating.
So how do you balance the two? If you've got an equation in which two things go in opposite directions,
well,
how do you quantify the two different effects?
Yeah, well, the heat is a very localized thing. They're heating just the region where the fires are, and the ash and soot will disperse and spread out, so that will cool over a much larger area. So the cooling effect by far dominates any effect from the heat from the fire. But the biggest factor is that you're taking that carbon as well, and you're putting that carbon back up into the atmosphere, the carbon that was trapped that was stored in the trees and in the soils also, because some of the soils can actually, peat, you get these peat fires, and you can get the soils actually store a lot of carbon. And when they're heated up, they're releasing some of that carbon also. The fire can burn into the soils depending on the carbon content and the heat of the fire, etc. But also, you're losing your carbon sink, right? I mean, you're losing the carbon sink, and people, have been very concerned with the, I think the Amazon fires have been in the news and are still in the news and will be for a long period of time, is because these are fires that are deliberately set, right? It's one thing if because of climate, if you're drying out forests and weakening the trees, they're more susceptible to disease and pests and things, and they're more susceptible. They lose their resilience. They lose the water content if it's dry, and they're much more likely to burn. There's more and more lightning, more and more storms, intense storms with lightning, which can then start these fires. In California, a lot of the problem was the Santa Ana winds would knock over power lines because the power grid was very flimsily built, and these power transmission lines would fall and then start fires. That's been a huge problem in there, California, from the high winds. But so you lose, but also people have been talking about the oxygen content, worrying about oxygen content because of the fires burning and so on. But, the oxygen is, we're at 21% almost of the atmosphere is oxygen. So the oxygen, when you have combustion, when you oxidize carbon plus oxygen gives you CO2, right? You're using up one carbon, or one carbon's involved and two oxygens are involved, right? So the oxygen, the rate that carbon is going up in the atmosphere is balanced by a drop of double that quantity of oxygen reduction, but the carbon's a trace element, CO2 is a trace gas, and oxygen isn't. So people do get a bit confused and worried. I mean, we're not going to run
out of oxygen.
No, we're not going to run out of oxygen.
Plenty of oxygen.
Yes.
That's okay. Good.
But there is a problem.
News to me. See, I had not heard of any upside of forest fires, because you've just given me some interesting food for thought. I had just assumed that forest fires are only negative things. They ruin our carbon sink,
Yeah.
and they create heat, and
Release lots of
the
CO2.
smoke wouldn't do anybody any good either.
Yeah.
So,
Yeah.
but now you're saying that maybe there's a more benefit. Are you saying that
No, I'm not
in
saying.
terms of
I'm just
global warming,
I'm
it's
not saying talking in terms of benefit or downside. I'm just talking about in terms of the physical, physical nature of what happens. And most forest fires are not hot enough to put ash and soot up into the upper atmosphere, right? They only put the materials in the lower atmosphere, and that gets washed out within about a week or so.
excuse my pushing you on
Yeah.
this, because I mean, the
It's a
people
rare
who
event.
talk
It's a
about
rare.
global engineering, the first
Yeah.
thing they think of is let's put some sulfur up there and block
Yeah.
the sun, incoming sun, so that it cools the planet.
Yes.
And what you're saying is that this soot will have the same effect.
If in rare case, it's very rare that fires will put up material up into the stratosphere. But there are fires that are burning so hot and intense and over such widespread an area, wildfires, that we're seeing that very thing happening. You can see the smoke plumes actually punch through the troposphere. Normally, when you see a large cumulonimbus cloud or something, it's an anvil shape, and that flat part at the top, that's the upper extent to which the convection can go, right? And that's near the tropopause, which is a dividing point between the lower atmosphere, the troposphere, and the level above the stratosphere. So you can see that anvil, that flat shape. Sometimes what we're seeing with these large fires now is we're not seeing a flat top. We're seeing the upward momentum of the smoke and heat and ash and everything is punching through and going up into the stratosphere.
Yeah, but you don't want to call this an advantage.
No, well, it's happening. I mean, whether it's happening. It's rare. It's with the most intense fires, but it happened with the Paradise fires, for example. It happened with the Fort McMurray fires. Okay, it's happening more often. It's a fairly new phenomenon. We didn't have fires that were intense enough to do that before, except we did have, when you have a fire, if you have a lot of combustible material and it's not all at the surface, directly at the surface. So I'm talking about cities with multi-story buildings, right? When a fire, when a city burns, like Dresden or Coventry or Tokyo, right? In the not nuclear attacks, but in these these conventional weapons destroying these cities in World War II, created fires that burned so hot and so intense and had so much combustible material that they created basically a storm, a fire storm, like a literal storm, where you can get rotation, you can get tornadoes and fire-nados generated, and you get tremendous uplift, enough to carry the soot and ash up in through the out of the lower atmosphere up into the upper atmosphere, and then it can start having climate changing events, right? If it's intense enough.
For example, fires in World War II, any of them had climate change?
I think so. Yeah, some of these firestorms. Yeah, I mean they basically. I mean, when you get this tremendous updraft, that air has to be replaced by air coming from the sides, and that air is high in oxygen. Of course, it's got the 21% oxygen, so it just creates this feedback, and you get this massive firestorm. And then if you have that situation, then you do get lofting up into the stratosphere. So it's just it's another way to study the effects of actual nuclear winter, and the effects of to better pin down how devastating any nuclear exchange would be to the global food supply, right? I mean, when the term was phrased nuclear winter, basically sunlight is blocked around the entire planet enough to stop photosynthesis, so plants die and everything else dies, including us, in a short period of time, with a large nuclear exchange. And then the research then went into more detail, and the climate models were better, and with supercomputers, et cetera. And it showed that you would require less and less nuclear weapons involved in an exchange for this effect to happen. So if there's a nuclear exchange between, say, India and Pakistan, you know, the entire world could go into famine, right? Massive famine.
Yeah, that
depending on, right? So that's the whole point of that. Now, the other point is that, you know, from these ideas, from these concepts, you know, if we can without a lot of money cool our planet with stratospheric aerosol injection. Okay, it's a form of solar radiation management. You know, we could cut down the amount of sunlight coming to the surface and cause a cooling of our overall planet, and figure out where to put the sulfur. Like this is going. I mean, I think that this will happen. I think that we'll end up doing this.
But won't there also be the effect of reducing the potential for agriculture? I mean, if you block the sun, you're not going to have as much food, isn't that?
Well,
but you know,
the agriculture is more. We're talking about a minimal blockage of a minimal reduction of sunlight, minimal, like far less than 1% even. Okay, so the effect on agriculture is much more dependent, you know, as long as there's sufficient sunlight for photosynthesis, and you're only blocking much less than 1%. So you're not affecting the growth of crops anywhere near as much as the droughts and, you know, massive floods in some places, you know, massive droughts and heat waves in other places. That's taking out crops. I mean, you talked about trees at the beginning, the need to plant. You said that there's about 3 trillion trees. How many trees were there about 100 years ago?
Apparently a lot more.
6 trillion probably. I would guess probably double at least.
Yeah, well, they're talking about, you know, the problem though is, I read a Yale University piece saying that a number of countries are undergoing big campaigns to plant 1 billion trees here or there.
Yes,
that's wonderful. But of course, 1 trillion is 1,000 billion. So
yes.
you have a long way to go before that really makes a difference. But they say that out of every 6 trees you plant, 5 of them are going to die because people have to go back and water them and weed them and whatever, and they don't do it, and so they die.
Yes,
so
I was going to say
really
that.
Then, if we want to get an extra 1 trillion trees to replenish the ones that have gone missing over the years, we need to plant 5 or 6 trillion trees, I guess, unless we better learn how to do it well and take better care of them.
Reduce the mortality rate. Yes, like the China Green Wall, for example, has about that sort of ratio. Yeah, they plant all of these trees and then most of them end up dying. There's also, I mean, there is some technologies where instead of just planting the tree, you know, you basically dig a cone-sized, a cone-shaped hole in the ground, and you put in the tree and the soil, you know, that is contained, and there's enough nutrients and there's enough water, and as long as there's water coming in, there's enough materials there to keep the tree going for 6 months. And if the tree lasts for 6 months surviving, then it's probably going to survive to, you know, much longer. It's probably past the critical phase. So there is different technologies of, you know, plant 1 trillion trees, but use technology where most of them will survive. There's also ideas of spreading seeds by drones, for example. Some people are talking about that. And all of these.
I did a talk show with the company in Britain that's doing the most of that. And I frankly, the more I look into the drone thing, the more I'm careful about not getting too excited about that. I don't think that there are probably times and places where it works, but I tell you what it does, I think is very interesting. Night before last, I did a talk show with a guy in India named Shubhendu Sharma, who invented something called the Forest company, and he has been promoting a methodology for forestry called the Miyawaki forest method invented by a Japanese botanist. And they do extremely dense. Oh, hello, cat. Who's your
Yes.
cat?
Yes, this is my cat. I can't go on the camera without him showing up and meowing. So
That's fine.
yeah.
Hello.
Yeah.
Very pretty cat. What's his name?
His name is Shackleton.
Oh, all right.
Yes.
Oh, Shackleton. Now
Yes.
you're down.
Shackleton the Explorer. Yes.
We got acquainted. So anyway, this guy has been developing little tiny forests in cities. You know, maybe a parking lot size. I mean,
Yeah.
parking spot size.
Right.
They put out 4 trees per for a square meter. And of course, most of them will die, but they choose indigenous trees of different heights, heights,
Okay.
so that they allow the trees to pick who gets to survive.
Right.
You know?
Oh, okay.
And they make a very dense kind of forest. So my notion is, with that kind of density, you could have, you know, local people take part in weeding and taking care of the forests and getting them going.
Right. Mm-hmm.
And I think people should dig up their lawns and put in these forests. If we planted, I read something saying that although corn is the crop that's most covered, you know, most acreage in North America,
right.
there's more land in lawns than in corn. So if we convert our lawns into forests, we would have a good start on the business of trying to replenish those
getting up the biomass, the plant biomass that will then photosynthesize.
I tried to get him to tell me how much carbon is being sequestered by his very dense, beautiful little forest, and he wouldn't tell me. He partly doesn't believe that the methodology that is used for calculating carbon sequestration is a very good method. He doesn't trust it. And partly, I think he has a philosophical objection to the very idea that the purpose of planting a forest might be for the carbon sequestration. He wants people to do it just because they're beautiful. Well, I think they're beautiful and they sequester carbon. And I want to find out how they measure carbon sequestration. Do you know what the procedure is for calculating that? Because I'm going to have to look it up.
Yeah. Well, I think that, you know, mostly it's kind of like, you know, if you have a plot, I mean, the best way to do it would be to get this massive scale and then, you know, put the, you know, like I'm thinking truck scales and, you know, that like a massive scale, and you put the soil on, you put the seeds on, you measure the weight change over time, right? You correct. And you know, you of course, water is going to add you know, greatly increase the mass of the soil and things like that. But, you know, you measure the change over time, and then you know how much carbon is going, you know, is going into growth of the trees. And then, you know, so you know how much carbon is being captured basically. But what they do is, you know, they generally have different areas where they're doing their research, and they'll measure like the heights of the trees and the width, the girth of the trees and things like that over time, you know, to get an estimate of the carbon captured. Or, you know, for different species of trees, they roughly can know how much photosynthesis based on leaf area and stomatal density, which does change depending on the precipitation level. It's you know, getting back to the trees, I mean, we really need to stop just thinking about what we can do on the land. The 29%, 71% of the planet is oceans. Most of the oceans are basically deserts for life, right?
Why? I mean, there's nothing stopping them from growing seed.
Well, the biggest factor is a lack of nutrients at the surface in the open ocean. Nutrients generally, when you get organic matter sinking and starting to be broken down below, then nutrients are released. So below the thermocline, a few hundred meters down in the ocean, there's tremendous numbers of tremendous amounts of nutrients. If those could be brought up to the surface, then there will be phytoplankton blooms. Then the zooplankton will eat the phytoplankton and the small fish all the way up the food chain, and you get a proliferation of marine life. And this happens naturally along coastlines, mostly, the West, like off California, for example, off, South America, right? You get the ocean currents, the North California current coming from the north, coming down the coast, and then because of Ekman flow, because of the rotation of the earth and the deflection of the ocean current, it pulls away from the coastline. That causes that water that pulls away at the surface has to be replaced by water from below. So you get upwelling from below. You get that upwelling and you get the nutrients brought to the surface, and you get the phytoplankton bloom, the zooplankton bloom, the proliferation of the food chain. And these are some of the most prolific areas for people to fish, on the planet.
Oh, I didn't know that.
Right? So these are the natural upwelling effects. So what I'm saying is, if we either provide the missing nutrients at the surface, mostly iron, there's large parts of the oceans they have loads of nutrients. They're just missing a few key ones, iron being a predominant one. So this is why iron seeding can stimulate phytoplankton blooms and then the growth up all the way up the food chain. But if it's in the open ocean, you can't have, you're missing out. So if you imagine having buoyant, like floating rafts, for example, or something, in the middle of the ocean with chains going down, supporting platforms at different levels, and you have this either feed in the iron, either seed the ocean there with iron or create devices that will bring up you could create wave-powered devices that bring up cold water from a few hundred meters down below up to the surface containing the nutrients, and then you can get the proliferation of marine life in that region. You can create an entire ecosystem out in the middle of the ocean floating, which will suck huge amounts of CO2 out of the atmosphere. So these things are, I think these things, I'm not saying not aim to plant huge numbers of trees, but, we need to look at the whole picture of how do we capture carbon? How do we take carbon out of the atmosphere? And when we take it out of the atmosphere, because there's lots in the oceans, right, which is causing the ocean acidification problem, if we take it out of the atmosphere, it's going to come from the ocean and go back into the atmosphere. So then we have to take out more, right? So if we take out huge amounts of carbon from the atmosphere, the oceans will release their carbon and we'll be removing that as well. If we take the CO2 out of the oceans in huge quantities by stimulation of marine life, for example, then the dynamic balance is different, and more carbon will start coming out of the atmosphere into the oceans, and then we're removing it. So it doesn't matter really if we take it out of the ocean or the atmosphere, it's the same thing. It's a benefit to us. It decreases ocean acidification, it decreases the CO2 levels in the atmosphere.
All right, my poor brain. Let's see if I can back up and get any of this. I assumed that what we would want to do is put as much carbon into the ocean as possible. You're talking about taking it out of the ocean? Okay,
I'm talking about the upper levels of the ocean. When you're talking about wanting to put carbon in the oceans, you're talking about you're talking about getting it into the oceans and then having it go down to the seafloor and become part of the seafloor sediments, where it's taken out of the. So it doesn't. When you talk about putting it in the ocean, you're talking about sequestering it in the deep ocean.
Right.
Right. When I'm talking about getting it out of the ocean, I'm talking about the surface layers of the ocean, which is where the ocean acidification is a huge problem because there's too much CO2 dissolved in the seawater.
Okay. So
right?
want to get it out, but where are you going to put it?
Well, for example, I mean, we've lost about for large marine fish, large marine creatures. We're down to 10% of what we had even 100 years ago. We've lost about half of the biomass on our planet. We're basically doing a conversion of we're converting all of the carbon on the surface of the earth into human beings, essentially, into our bodies, right?
Yeah, I hadn't thought of it that way, but
and chickens as well, right? Not just chickens and cattle
mm-hmm.
and humans, right? You know, a few separate species. You know, before we had so much more biomass on the planet in terms of plants and animals, and we've cut those numbers down. I mean, even to like a 100 or a few hundred years ago, there used to be so many fish in the ocean that people could almost walk from one island to another on top of the fish. Mm-hmm. This is how people talk, right? On some of the islands, and okay. We've depleted the oceans of so much of this. And coral reefs, you know, when they go, think of the biodiversity and the loss of marine life from coral reefs. So the idea of creating floating platforms, you could think of even creating coral reefs and things, right, in these regions of the ocean that are devoid of life right now. So the carbon initially goes into the bodies of these, you know, 90% of the plants and animal increase that we create. And but the carbon doesn't stay there, right? The carbon, they all die or they excrete. And that waste then goes down into the bottom of the ocean, right? The seafloor, mm-hmm. right? And then it gets captured in the sediment. So the carbon doesn't, you know, the carbon that goes into plants and animals is not there permanently. A lot of that eventually will go into the sediments on the ocean floor, where it is captured for a long period of time.
Okay, now let me back up, because I'm trying to work on this. You want to take the carbon out of the top layer of the ocean, and where are you going to put that? You want to send it quickly down to the bottom? What are you going to do with this? Because I can see the logic of wanting to make more room in the ocean so it can absorb more without.
Right. Okay. Well, the first thing is the carbon that's just floating loosely in the ocean or in the air ends up going into the organic matter that makes up plants and animals that you get a vast increase in the biomass of plants and animals. So that's where the carbon goes initially. And then
you want these platforms, and tell me again what these platforms are going to do.
Well, you're going to create, you're going to stimulate a massive growth of marine life in a region where there's very little marine life. In fact, it's termed a marine desert, if you like.
That's because we want the seaweed.
We want to capture huge amounts of carbon. And also we need to feed a growing world population. So, you know, there'd be a huge proliferation of marine life around these regions. Fishing, you know, and some of it could be fished out and used as food for people. Mm-hmm. Right, mm-hmm. The growing global population.
It's also going to help the acidification problem
Yes, it will also remove the CO2. Yes, and help with that problem.
Right. Now,
you know, it's just that we always think of doing. You know, I'm not saying don't plant 1 trillion trees, but I'm saying, you know, if we want to remove carbon from the atmosphere quickly in huge amounts, then we need to look. You know, we can't ignore the ocean. Right.
Well, great. Yeah. I tell you, I think everybody has a hobby horse. My current hobby horse is the tree issue. Yes. But certainly sounds like yours is this ocean thing. Yeah. Tell me how realistic that could be. In other words, how long would it take? How much expense would there be involved in doing it? How would you organize actually within, say, 10 years, creating structures that would do this thing that you're proposing? Because this is all new to me.
Yeah, well, we do it in steps, right? I mean, I think the first step is to stimulate phytoplankton growth in the ocean, right? And that could be done tomorrow. Go out there with the ship with iron sulfate, or, you know, even better, put the iron sulfate, inject the stratosphere with the not just sulfates, but iron sulfates. Okay, and then the sulfate can actually act to block some of the sunlight. The iron will eventually fall into the oceans and stimulate phytoplankton growth. So it's like 2 for the price of 1.
Okay.
Right?
I haven't heard that one before.
Right?
You must have opponents.
ISA, iron salt aerosol. Yeah, I'm going to kind of pivot a bit with some of my videos to some of these solution videos.
Please, because I think that's really what we need to be doing now, is looking at what are the steps that can be taken kind of on an emergency basis.
Yes, exactly.
If the IPCC, this report was right, we don't have very many years. So we better get cracking. And I am interested in trees just because theoretically you could plant an awful lot of them right away.
Yes, right. Yes, it's very quick. Now, you also, I think in the Arctic, I mean, it's sort of a chicken and an egg thing. Like the permafrost, you can't grow trees in permafrost, right? If the top layer is thawed out, then you have some soils. Then you get organic decomposition. You get the microbes. They produce CO2 and or methane, depending on the absence or present or lack of oxygen. And then once you have the soils, then you can get the trees starting to grow because they can support trees. It's not just an active layer which thaws and freezes every year. So then you start getting trees growing. And then once you start getting trees growing, then yes, there are feedbacks that increase the temperature of the soil because that's benefiting the trees that are growing. And then you can get more trees growing and more trees growing. So it's not like the trees aren't heating the soil initially, right? The heating is from the, the huge temperature rises in the Arctic. And you're right, there's vast areas of Siberia that were once the tallest thing growing was little shrubs, a decade ago. And now there's larch and pine and tree forest, with trees 3-4 meter in height, like within a decade, right? And the albedo is completely different because now when it snows, the snow goes between the leaves of the tree or, maybe initially lands on trees or pine needles and then falls off quickly because they're dark surfaces and the sun would penetrate the snow, heat up the dark surface and then the water would drip off even below 0, right? Just from sunlight. So the albedo of these areas that used to be white, once it snowed, are now darker. So that will also contribute to a darkening Arctic and a temperature amplification in the Arctic. So you're absolutely right that so planning, we just have to basically look at the distribution of trees, say 100 years ago and try to get back to that type of situation. So huge planting programs of trees in the Arctic, I don't think is definitely not the way to do it.
We do know that planting trees in, let's say, Brazil is a great idea, and that planting them at near the North Pole is sure not a good, and the Arctic is not a good idea. And we know that half of Canada, or a little over half of Canada, gets some permafrost so someplace, let's say, take a given tree that would grow in any different climate, and if you go north from the Brazil to this north, there's going to be a transition zone in there where someplace in our boreal forests of Canada or in the taiga of Russia, there's going to be a zone in which this tree stops being a beautiful asset to humankind and becomes a threat to humankind. And so far as I can tell, nobody can tell me exactly where that zone is because there's a lot of boreal forest that gets permafrost some of the time and not all the time. And therefore, during that period, that zone, it could be an asset when it's sequestering carbon, but then you go further, and if it's actually warming the soil, then its negative impact is greater than the asset of its
the positive. And also to throw a wrench.
I don't know how to find that out.
Well, to throw a wrench into that is also those zones are shifting because of the climate changing. Right? They're shifting. Zones are generally moving towards the pole. Right, as the poles warm faster than the equator, the zones are shifting away. Those zones, are very dependent on the atmospheric circulation patterns, because those determine the, so I'm talking about the jet stream locations and the areas of, I'm talking about like the Hadley cell. I mean, you can think of the Earth divided into 3 cells, if you like, from the equator to the pole. The Hadley cell from roughly 0 to 30 degrees north latitude.
You're going to have to explain that to me. I've heard the expression, but I don't
The
know.
ferro cell is 30 to 60, and then the polar cell 60 to 90. And
Sorry,
you can get
these cells are
these
sections of the geography.
well, the cells, like the Hadley cell is important because, the air rises at the equator, right? Hot air rises. So the hottest air is at the equator. It rises. It carries a lot of water vapor. Then as it moves up, then it spreads out and it descends basically around the 30-degree latitude mark. And where it's descending, you get air from high altitude is very dry, very little water. And then it descends to the surface around 30 degrees and it's bone dry. This is the region where the world's deserts are. Okay, so these patterns create the bioregions, right? So the deserts of the world, look on the map at where the deserts are. They're all centered somewhere 20 to 40 degrees, 25 to 35 degrees latitude. And they're because of this Hadley cell rising and descending, right? So the problem is with climate change, with overall warming, then the cell can start descending in different places. Further north, for example, instead of 30 degrees, maybe 35, 37 degrees. So the deserts are expanding northward. This is a huge problem in Europe because it's very possible that as climate continues to change, accelerates, that the deserts, the Sahara, the deserts of northern Africa will actually cross into southern Europe. And I think we're starting to see this sort of thing happening with some of the heat waves there and some of the dryness in places like Spain, and those regions. So this is a huge problem. Now, when we had European heat waves, there were 2 bad cases this summer. The second one, the heat wave, the jet stream ridge went up from the desert over Africa into Europe, caused that heat wave. And then it continued and went right up and covered Greenland for a period of time. And we had massive and record melt in Greenland right before that whole system dissipated. So the pattern of heat, like heat is basically moved from the equator. About 2/3 of the heat is transported in the atmosphere, about 1/3 by the oceans. Okay, so
you could move the Hadley cells. I have no idea where they are or how that works. If it were possible to change that, what would you want to do? Would it be theoretically? I mean, if we were
okay, it's clear.
Would we get the Sahara to green again?
Well, what we'd want to do is we need to cool the Arctic, right? If we cool the Arctic, then that will restore the jet streams to a configuration that is more conducive to what we're used to. Okay, so I mean, the Arctic is warming so much faster than the rest of the planet. It's just it's unbelievably how fast the warming is, and that basically weakens the jet streams and makes them wavier and is causing all these extreme weather events. So no, it's pretty clear. I mean, to restore a stable climate, so you'll hear a lot more about climate restoration. We need to cool the Arctic to restore a stable and healthy global climate. And then the jet streams will go back to how they behaved before.
No, but your recipe for cooling the Arctic begins with shooting iron sulfate into the stratosphere. Is that your secondary solution?
Well, that's one method. People are looking at, just restoring the sea ice.
How do you do that?
Well, there's a company called Ice 911, for example. And they're talking about little tiny glass beads.
Yeah, I've heard that. That sounds very scary to me. The fish will eat the seeds, the glass beads, and then you and I will eat the fish.
Well, the glass beads are of the size that they're produced. They already exist. There's trillions and trillions upon trillions of these glass beads already in the oceans. They
Where?
make up the skeletons of diatoms, basic phytoplankton. Like diatoms, they make a skeleton out of silicon dioxide glass, right? Very intricate skeleton. That's part of the diatom. It's microscopic, right? They're little tiny plants. The other types are calcium carbonate based skeletons, like coccolithophores or foraminifers. There's other types of phytoplankton that make up calcium carbonate backbones. Those are the ones that are threatened the most by ocean acidification, because that dissolves those calcium carbonate skeletons. But the diatoms, which are most common, say, in the Arctic, their skeletons are tiny, tiny glass beads. So you make these beads the size of the diatom beads, and you spread them on snow and ice in the Arctic, and they reflect a lot of sunlight and they keep it that snow and ice brighter, and they reflect sunlight and allow the ice to come back, to not melt out. They make it a lot more resilient. That's the idea.
Yeah, I've heard of it before. And
Yeah.
day before yesterday, I think there was a conversation on the Pugwash listserv about these glass beads again. Which,
it sounds. I agree. It sounds terrible, but we're talking about, you need to. The devil's always in the details, and the beads exist in nature by the gazillions in the skeletons of diatoms. So when the diatom dies, the weight of this skeleton, it pulls it down to the ocean floor where it becomes part of the sediments.
So we don't have to worry about eating glass beads.
Well, look, go on a sandy beach, right? Sand is silicon dioxide.
I don't eat the sand.
No, but I mean, but think of the sand grains on a beach, right? We're talking about making them much, much smaller, because the smaller they are, the more highly reflective they are. Right. So that's just, we're just touching on a couple different ideas.
All right.
But the point is in order to restore a stable climate, we need the circulation patterns, air in the atmosphere and oceans, to go back to what they were before, say 100 years ago. And in order to do that, there's only we need to look at the change in temperature on the Earth in that 100 years. And the Arctic has warmed like crazy compared to the rest of the planet. So if we cooled the Arctic like crazy and got it to its previous temperature, we would restore the circulation patterns of the ocean and atmosphere and get back to a much more stable climate.
Okay.
It's simple. It's like the concept is simple, right? Doing it, of course, is harder, but we have to understand what we have to do first, and people can't get over that step, right? You have a lot of environmental people saying, oh, we can't, they're saying on one hand, we've got 11 years and basically that's it, climate emergency. And then on the other hand, they say that doing something like cooling the Arctic is too risky, right? Where's the logic break in that?
Yeah, I agree.
Right. The logic break is pretty. A lot of people just are not thinking clearly at all on what's happening. Like they get too emotional and caught up, and throw up their hands. Oh, we're doomed, and yet, oh, this is too dangerous. Well, wait, you just said that we were doomed. So what's the? Are you worried that, if you think we're doomed in 10 years when we do this stuff, maybe it'll be only 5 years? Like, what's your concern? Like, seriously, you have to just ask people, and they have no answer. They haven't thought about it clearly.
Well, I'm all for being as disruptive as possible. It sounds like you are also. So we're partners in crime on this. I'll be back in touch with you, because I think you certainly have some far out ideas, really bold notions. Keep me posted as you develop further ones. Okay.
Okay, thank you.
And this has been a wonderful conversation.
Yes.
Thank you.
Yeah, we'll do it again in a month or two. Okay, thanks.
Terrific. Bye-bye.
Goodbye.
This conversation is one of the weekly series Talk About Saving the World, produced by Peace Magazine and Project Save the World. Please visit our website at tosavetheworld.ca, where you can sign the Platform for Survival, a list of 25 public policy proposals that, if enacted, would greatly reduce the risk of 6 global threats to humankind. Come back next week for another discussion of a serious global issue.